Hello, I'm Pablo. Thank you for your interest in our work on open vocabulary attention maps with token optimization for semantic segmentation in diffusion models. In this video, I will give you an overview of our work. So I hope you find this work interesting and, I look forward to seeing you at this year's Computer Vision and Pattern Recognition Conference where this work will be presented. Thank you and let's get started. The introduction of diffusion models have changed the paradigm of how we generate synthetic images using text description, opening up new possibilities for using this data in downstream tasks in deep learning. These models operate using a diffusion process that denoises an initial random state until it synthesizes a final image. During this process, the semantic information from the text description is incorporated to guide the denoising. This research addresses the question of how we can extract the influence of this semantic information for tasks such as generating synthetic images with semantic segmentation masks. This is crucial for training models in scenarios where data scarcity is a problem, as well as for interpretability purposes to understand the underlying mechanisms of these models. To tackle this problem, previous works have focused on the cross-attention mechanisms in these models, particularly in architectures like stable diffusion, which we will focus on this paper. Cross-attention mechanisms weigh the influence of the semantic information from a text prompt across different parts of the resulting image. Because of this, they have been successfully used for interpretability purposes and for extracting segmentation masks, either directly without additional training or as input features for other trained models. During the diffusion process, the cross-attention blocks yield attention matrices. When aggregated, these matrices produce informative heat maps that shows the influence of a token or a word from the text prompt on the resulting image. However, the direct use of these attention matrices is constrained to the words in the text prompt, which is limiting for tasks like open vocabulary semantic segmentation or understanding the influence of words not explicitly influencing the prompt. To address this, our work proposes a generalization of these attention matrices, formulating open vocabulary attention maps. To tackle this, we propose the introduction of an additional attribution prompt to act as a semantic description for the attention maps used in generating segmentation masks. To compute these attentions, we project the new prompt to obtain the keys of the attention mechanism, which contain the semantic information. We then merge these keys with the queries yielded during image synthesis, generating attention maps for any arbitrary token or text. This approach removes the restriction imposed by the direct use of attention. However, another question arises when we want to use these attentions for computing semantic segmentation masks. How can we choose the attribution prompt to segment any given class? We propose to learn a specific embedding for each class in a semantic segmentation task through token optimization. For doing this, we optimize the open vocabulary attention maps with respect to the attribution prompt, using a semantic segmentation loss for the optimization. Doing this, we found that this lightweight process, which can be used with just a single annotated image, generate tokens that transfer this information and provide attentions for segmenting other images. Finally, to measure the quality of the attention maps, we binarize them using a training-free procedure similar to those used in concurrent works. This process is based on 3 steps: a self-attention refinement, a thresholding, and the application of conditional random fields to improve the mask quality. In this example, we can see how using a token optimized on other images boosts the quality of mask generating from the attentions. For evaluating our method, we perform 3 main experiments. First, we evaluate the mean intersection over union of the mask generating used in our proposal with and without optimization. and compare it with state-of-the-art methods based on the extraction of attention from Stable Diffusion. We found that our method, which uses only a single training image for each class, obtain comparable results to other work that require more data and expensive processing. Second, we evaluate the performance boost of the optimized tokens in mass quality. To do this, we adapted compatible words based on similar paradigms on Stable Diffusion and found that the use of optimized tokens increased the quality of the mass for all test methods. Finally, we trained a semantic segmentation model on synthetic data and found that the increased mass quality is transferred to the model performance. To recap the contribution of our works, our proposal generalized the current framework by formulating open vocabulary attention maps, removing the dependency on words within the text prompt, and also this shows that words do not need to be explicitly included in the generation prompt to create informative attention maps. Second, our token optimization approach highlights the importance of the semantic descriptor used for generating the attention that describe an object. This allows us to improve the performance of a state-of-the-art method simply by changing the input descriptor. Finally, we provide an implementation in the form of a Python package compatible with different versions of Stable Diffusion. Thank you for watching. I hope you found this work useful, and we see you at the CVPR. Thank you very much. Bye.